Okay. Yeah. Hi, everyone. Is the sound okay? Yeah? Okay. Thanks. My name is Luka Jacobowitz. I work at CodeCentric. I also do a lot of Scala stuff in my free time. I've recently been named a maintainer for the CATS library, which is a real honor. And I'm also really honored to be here. So this is a beginner's talk, if you can call it that, I guess. But it's about referential transparency and what referential transparency can do for you. First up here, who actually knows exactly what referential transparency is? Like just a hands up. Okay, well, that's a few. Okay, that's perfect because you guys are my audience, right? Okay, so first question is exactly that. What exactly is referential transparency? So how many of you know the concept of purity and pure functions? Can I get hands up? Okay, well, basically these two things are exactly the same. Referential transparency is mostly synonymous with purity, meaning the complete lack of any side effects, right? So how do you define a side effect? Is anyone here completely certain that they can define the exact definition of a side effect? A few, okay. These are the things I'm trying to teach, so this is perfect. Okay, as functional programmers, and we're on a Scala conference, so I expect most of you to call yourself somewhat of a functional programmer. We want to avoid all kinds of side effects. But the question is, what exactly is a side effect? And some of the common things I hear when I ask these questions to colleagues, for example, is that a side effect is something like when you mutate something, or it might be a function has no side effects if it always returns the same thing given the exact same input. And these are pretty good definitions, but they're not complete, right? There's a lot of other things that can go on. And I'm going to show you this right now. So what do you think of this function? It's a very simple sum function. It sums all the integers in a list. But it also does some nasty thing called launch nukes. We don't know what it does. We can guess based on its name. But in essence, if we apply the definition, the second definition around here, does it always return the same thing given the same input? Well, kind of, right? But it also modifies the external world. So this definition is pretty incomplete, right? Because this kind of returns the same thing always, but we also get this, well, side effect in here. So this sum function is not pure unless launch nukes literally does nothing. Then okay, but yes. Another function is this, right? This is like maybe how a Java programmer would write a sum function when he starts writing Scala. There is a variable right here, and most of us could see that we could definitely write this with the fold left we saw right here. But I'm actually going to say, go out and say that this is actually a pure function if you consider the whole block, right? So the individual expressions inside here, they're not pure. They're not referentially transparent. But the function, as considered by itself, is actually pure. And to see that, I'm going to give you the definition you've been waiting for. And that is that referential transparency just means that exchanging a term for any other term that refers to the exact same entity does not change the program in any way. Well, this sounds super complex, but I'm just going to show you an example. And if you've been to Daniel's talk, he had a very similar example, and I didn't steal it, I swear. Actually, there. Exactly. And the question is, are these two programs equivalent? Right? So here we have a sum of list 1, 2, 3, and we add it to another sum of list 1, 2, 3. And we can see here that this is duplicated. So we should be able to inline the call and call it x, de-inline the call, sorry, and just call it x and memorize the result, basically. And then x plus x should be the same program as the program above, right? And we can see that for this function, it totally works, right? This is the exact same. But in this function, we might launch the nukes once or twice, and that's a complete different program if you think about like a nuke launching program or something, right? Okay. So this is the definition for referential transparency, and this is the test you can do in your head. Like, is this going to change if I just swap the definition out for its name, right? So here I have the name x, and in a referentially transparent program, I should be able to swap out the x, every x that ever occurs for its definition, right? So this is what we talk about when we talk about equational reasoning, right? So in mathematics, for example, every time we encounter an equal sign, these things have to be exactly the same, so they can be swapped out however the hell we want, right? And if we write in a referential transparent way, it should be exactly the same, right? Okay, so why would we want to do this, right? So we've probably heard about pure functions as cool, but like what do I get out of this? Why do I have to constrain myself to these arbitrary, in quotation mark, rules? So the first thing is that testability, right? So we all know that, I'm not going to assume, but I think that pure functions are massively easier to test than doing testing when you're having a lot of mutation, you're having a lot of implicit state. And I'm going to argue that completely restricting any side effect is just going to make this easier and easier, because sometimes you have some kind of implicit effects. For example, you write to the console and then you do some other effect, and now your code depends on the order of evaluation. If we have no side effects, then there's no implicit ordering of any evaluation, because these things don't happen implicitly, but explicitly. And this is exactly this point. Know when and where our effects occur, right? So if we have any effects at all, which we're going to come to later, we will know when or where or how they occur. And this can be very, very useful when you want to reason about your program and you want to find out why is my program writing to the database here? I'm like, I don't see the call. But when doing pure functional programming, you will see exactly where and how this happens. And yeah, and this also applies to the compiler, because if you think about it, when your code is guaranteed to not have any side effects, the compiler could make a lot of potential optimizations, but also it could make refactoring a lot easier, right? So if you can say that the order of execution doesn't matter because we don't have any side effects anywhere, then we can just refactor anything out and in. And like I said, with swapping out values for their definition, this can be very, very simple. And I'm going to talk about a lot of these potential optimizations next. It's probably a good time to note that Scala can't do most of these because Scala is not a purely functional programming language. And if you look at things like Haskell or PureScript, they do some of these, but not all. It's still very much a work in progress because it's not very popular. So, but potentially these are all optimizations that could be made when you have a purely functional language or a purely functional system inside of another language. So the first thing is memorization, right? We already saw that with the sum function. If the compiler knows that these two things can be swapped out, then the compiler can make these optimizations completely for us, right? We don't have to think anymore. We don't have to sum up our lists twice, because the compiler said, oh, I already ran this for these kinds of arguments. So the compiler can just say, OK, I'm not going to run it again because I already memorized it somewhere. And The next thing is parallelization, right? So if our code is completely side effect free, then we don't have any shared state, and we don't have any ordering of any we don't have any implicit ordering of any effects, right? So this means that it doesn't matter how our pure computations actually run. They could run completely parallel or sequential. The result of the computation is the same. So we could do a lot of parallel computations without ever having to worry about deadlocks or data races or anything of the kind, because the compiler could do this completely for us. And another very cool thing is common subexpression elimination. And does any of you maybe know the JavaScript partial evaluator prepack? It's something the JavaScript community at Facebook came up with, and basically it's, well, a partial evaluator, right? So you have a lot of JavaScript code, and you want to optimize it as much as possible, because JavaScript is basically nowadays the bytecode of the web. And what this tool does is it looks at your code and looks which of the JavaScript parts can already be evaluated at compile time, right? And if you think about it, every single expression can be evaluated at compile time if it has no side effects, right? So if we have a lot of pure computations that don't depend on any runtime values, all of them can be completely evaluated at runtime, which would potentially save us a lot of different kinds of performance problems that we don't have to anymore defer to the runtime, because they can happen at compile time because they don't depend on any runtime values and are completely pure. So these are some of the cool things that could enable us to do a lot more sophisticated and efficient stuff in the future, I hope. Okay, so the question is, how can we, or why, the question was why we should do this, and now the answer to this is, of course, that effectful and non-effectful code should remain separate at all times, right? And we know that, for example, Haskell, PureScript, these kinds of languages already do that, but how could we do this in other languages? And I've got a few examples. For example, did you know that C++, I think 11, has a term called const expression? And basically, const expression can be any function that can be run at compile time. So it's basically exactly what I talked about. It has to be a pure function. It's basically an annotation you give to any function, and it means that it can be completely optimized away at compile time. And in the same way, Fortran has something called pure function, and D also has a pure annotation you can give to any function you want. So these are some examples from real-life languages that are already out there that are not really considered functional, but they're already applying these because they know it can give them performance benefits. So, but what do we do in things like Scala? Like maybe in Scala it might be better for us if we didn't have purity annotations but impurity annotations, because we want most of our code to be pure, and the code that is not pure we want to annotate that way. So maybe we could at some point define this somewhere in the Scala compiler, that we have this impure keyword. So we have this impure def launch nukes, and now we know exactly, okay, which code is impure and which is pure, and then the compiler could potentially do all these things for us, right? The problem with this, though, is that if we look at asynchronous code, then we have a whole nother problem. And if you've seen Daniel's talk, he talks about this a lot. Then you realize that async and side effects, they're mostly sides of the same coin. So we could do something like this, async impure def, and then like something like async await, but those people of you that have worked with async await know that it's very similar to something called for expressions in Scala. So let's try something different, because we don't want to add a new language feature for every different kind of effect, because most of these have already been solved in a way. But I'm going to try to derive the solution step by step. So what we want is that our effects are not happening to the side, right? So we want to separate them. We don't want them to just happen at any time. We want to somehow combine them. They should be first-class values, and then we should supply them to our main method, and then the main method should run them all, which we call at the end of the world, basically. Which just means that we don't call them inside our pure computations, but only at the end. So how could we do this? One very simple idea is like, okay, every side effect is probably just a function to unit, right? We do something, and then basically we can just have a list of all of our side effects, and then we just give it to our main method, right? This is the potential main method of the new Scala, where side effects are more important. But many of you can probably already see the problem with this. Does anyone see the problem with this? No, okay. The problem with this is that what happens if you want to make a database call? What happens if you want to get something out of local storage, for example? If we only have a function 0 to unit, then we can never get anything that happens through a side effect, right? So calling into the database is a side effect, but we also get something back. So we need to add some kind of return type. So I don't know, let's try something a little bit different here. So this is a little bit better because it allows us to do the things we want, but it's also really ugly because we have here, now we basically model our effects not as a list of function 0 to unit, but as a function from any to any. And we could potentially perform these side effects by just folding the lift and just applying the function every time. And here we see an example for the new main method. Basically, it is a list that gets an item foo out of local storage. Then we take this foo in the next function, right? Because the function is from any to any. We can take it and then print it. And then we can also potentially do other kinds of effects, right? So the next effect here is to get the new date, because getting the current year, for example, is not referentially transparent because it could change. It depends on some outside force. And then at the end, we also want to print out. So this is a very, very basic program. But we already see a problem that, for example, we don't have access to foo down there. So this is already, this has two problems. And one of these is that it's completely stack unsafe. And the other one is, of course, that our effects are modeled as any to any, and we lose all type safety. And this is really bad. So let's try something different. Let's try to model our effect as something like this. We have an effect type, which we call effect, and it has a single function called chain. In the chain function, we take the value that is returned from the side effect, and we use it to produce a next effect, right? This is the function f. It takes an a and returns an f of b. And then the whole computation returns an f of b. And here we see a very small example for this. This is our new main method of type effect unit. And we see here that local storage get item returns, we don't really see it, but it's implicit. We can tell that it returns an effect of type, whatever type foo is. And then we can chain it with a new effect, which is put string line. And that will return an effect of unit. So the whole computation is of type effect unit. And if you've paid attention to some of the things, maybe this function signature seems familiar to someone, maybe? Flat map, exactly. So this is basically, very basically, the idea of the I/O type, right? So with an I/O, we can flat map to chain different types of effects together. And here is a small example that uses Scala's for comprehension, which desugars to flat map to well, to get our program going, right? So here we can see that first we get the foo from our local storage, then we put it out then we print it out to the console, then we get the current year, and then at the end we print it all out. So this is our program, and it's completely referential transparent, and it uses the I/O type, and we get type safety, and we could implement this in a stack safe way. I'm just going to defer to Daniel's talk again because he knows exactly how to do it. But essentially, we accidentally invented monads, right? So we tried to get some kind of effect, and the only real good way to get effects that we've found thus far is by using these monads. Of course, it's not the complete definition of monad, but it's the most important part of it, the flat map or the bind function. There's also monad laws that I have to mention for completeness sake, and the pure function. But essentially, monads do exactly this. They chain computations together. And side effects can also be really, really greatly changed together by using these monadic comprehensions. Okay, so here is a small example for how some could maybe implement it. This is again not stack safe, but here we see the class simple.io, and it has a small thunk in here called unsafe run, and we can implement flat map by just returning a new simple.io that, as its unsafe run function, returns a function from nothing to we apply the function to our own unsafe run. So this, I'm not sure here, this returns an A, right? And then we apply our F. So this returns a simple IO of B, and then we unsafe run it. So this whole thing returns simple IO of B. And this is a very simple implementation, but it works because it defers our side effects. So we could potentially use this for our real-world programs, but I advise you not to because, as I've said before, it's not stack safe. And if we want to lift a pure value into this IO type, we can simply do it by returning the function 0 to an A here. Does that make sense to everyone? Yeah? Just nod your head? Okay. Okay, good so far. So the takeaway here is that monads allow us to treat computations as values that can be passed around as first-class citizens within the pure host language. So Scala is not exactly a pure host language, but it can be, right? So if we are strict about this, we can make Scala a pure language with the IO type to model all of our side effects. Okay, so where could I potentially find this in real life? Cat's effect IO is probably the most sophisticated answer to this simple problem. We heard from Daniel just now again. I keep repeating myself, but exactly. But there's also a Monix task which goes a bit further and has these finalizers built in. So the whole problem which we saw about Scala Z7's task, Monix task, it has solutions for this kinds of things. And then there's also FS2, which offers some additions to the cat's effect IO task, the cat's effect IO class, but it also offers streams, so you can get resources multiple at the same time. You don't have to get one resource at a time. You can get multiple resources at a time, and it's all resource safe, and it has a lot of very sophisticated stuff. If you're interested in doing pure functional programming I think FS2 is one of the best ways to do a lot of these I/O things. And yeah, so concluding, I'd like to say that eliminating only some side effects, as a lot of Scala programmers do right now, can only get us so far, right? To get the safety we actually want, we should be fully embracing pure functional programming, because it allows us to achieve the safety that we're actually looking for. Okay, and with that, I'd like to thank you for listening. You can find my Twitter at Luka Jacobowitz. And are there any questions? Yeah, sure. Sure, go ahead.
Logging is a side effect.
Yes, logging is a side effect.
So how would you advise to treat it?
Logging?
Do we
What?
have a log monad? Or
You can do logging in the I/O monad. We've seen here that, for example, here this put string line, you could log in the same way, but it's not nice. I agree with you, but there are some ways. For example, there's the final tagless approach, which allows you to basically define certain computations as abstract types, and then you can implement an interpreter for it. And in the interpreter, you can do the action and also do a logging call for it. But you could also do it with I/O in the same way, right? So if you say, I want to call to the database, you could say, okay, I just have an I/O that makes a call to the database, but you can also have an I/O that makes a call to the database and also logs this call to the database. So it's definitely possible, and usually when you want to log something, you're also doing some sort of side effect at the same time. So these things, they work together, basically.
you mean we should ban any logging inside the...
Yes, that's my point. Yeah, do everything that is not referential transparent in this I/O monad.
Okay.
It sounds extreme, but I don't know. If once you get used to it, it works for most people. Sure, go ahead.
How do you manage resources and how to close it for comprehension?
Closing resources. Yeah, so the question was, how do you close resources? And this is exactly a problem that we have with I/O. With just the simple I/O type, you would have to do it manually, right? But if you look at something like Monads or FS2, they have a lot of these extra things that you can use to do resource-safe side effects, right? So Monads has finalizers basically built into the Monads task type. So something like if you want to run two computations, two side effects in parallel, and for example, you want to cancel them both, then it will also free all the resources. So the I/O type is just like the very, very base type. If you want resource safety, use something like Monads or FS2. They're both very awesome projects, and I can only recommend them. Sure.
Just in this particular example, you do local storage get item, so
Yeah.
it's supposed to return an IO.
Yes.
That possibility is always a future, and then it starts having a problem.
Yes. So the problem with future is that it is not referential transparent. But for example, Cat's effect and Monads, and I think FS2 as well, they all define methods that allow you to convert a function that returns future into a function that returns an I/O or a Monads task. The problem with future is, of course, that future is not referentially transparent in the way that it eagerly evaluates any side effect that might be inside the future, right? So if you get a future that makes a database call, you don't have to run it. It just automatically, implicitly happens. So it breaks referential transparency. Yeah, that's basically it. So this talk also entails like the fact that you shouldn't use future. I advise against it because if you want to use pure functional programming, that is. Okay. Any other questions? no, then thank you again. Like I said, you can find me on Twitter. Be happy.